Welcome back to ECE 320A. A lot has happened since we last met. You have two assignments that are due rather quickly. One is due Sunday and the other one is due a week from today. And they cover essentially inverse Laplace transform material. The last problem on homework number 5 is dealing with final value theorem. Have you seen the final value theorem before? It's not the final value. We'll talk about that hopefully on Thursday. But today what I want to do is focus mostly on, all on inverse Laplace transforming and partial fraction expansion. Exam number 2, as a reminder, is a week from Thursday. And do you want a review session? Is the same time as before? Oh, that's not. Okay, I'll try to put some times that you can vote on D2L, and then we'll see if we can get a room or get some kind of response on that. I have just recently posted a few more practice exams for exam number 2, and the ones that are there from the summer, just don't get too worked up with the topics. They don't necessarily overlap with what we're doing now in the fall semester, but I think the fall and spring, the total semester exams are more representative of the material that we are going to be covering. We're essentially covering chapter 12 and some of 13 when we talk about poles and zeros, but I think you're okay with poles and zeros, or I hope we will be quickly okay with poles and zeros. What I want to talk about today is the inverse Laplace transform and the partial fraction expansion. That's the way that we will inverse Laplace transform. And we're separating that into two different cases. Case 1 is when we have distinct roots. That means we have, if we are looking at the x's in the s-plane, then we only have unique x locations. We don't have x's lying on top of each other. That's what I'm meaning by distinct roots. If we don't have that case, then we have repeated roots, and that means we only have to have one root that might be repeated. Then we're falling into case 2, and hopefully we will get to that today. We better. And in that case, we will show different techniques for computing these numerator constants or these residues or the partial fraction expansion coefficients. I might call them either of those phrases, but you can use those techniques in case 1 also if that makes you, or if you like that particular approach better than another. Let's then get started. If you do this partial fraction expansion, it's valid for all values of the complex frequency variable s. You can substitute any particular value you want for s. As long as it's not at a pole location, then you essentially will get infinity equal infinity, and that's not going to tell you anything. But if you select a value of s that might be meaningful, then you can use that to your advantage when you are performing these partial fraction expansions. I want to start today with this particular example, and it's falling under case 1. It's distinct roots, and now we have a numerator polynomial and a denominator polynomial given as on the screen, and there's our capital F of s, which could correspond to a voltage, a current, a velocity, a temperature. We're just keeping it as a generic capital F of s. We now want to find little f of t, and that's the inverse Laplace transform of capital F of s. What's the first step in that process? If we want to find, so in this example, we are looking for f of t, which is the inverse Laplace transform of capital F of s. What's the very first thing you want to do in finding little f of t? You need to check to see if this particular transform is strictly proper. You need to make sure it's strictly proper. And so now is f of s strictly proper for this particular capital F of s? Is it? And I think I heard most people answering yes. If you wanted to verify that or check that, what did you actually do? I'm assuming you checked the degree of the denominator. That's what I'm labeling as capital D of S. What is the degree of the denominator? Third order, isn't it? We have an S squared times an S. This is now 3. And we need that to be less than the degree of the numerator. I'm just checking to make sure you guys are awake. This needs to be greater than, thank you, the degree of the numerator. And what's the degree of the numerator? 2. So 3 is bigger than 2 the last time I checked, and so we are okay. Now we can break it apart or put it into a partial fraction expansion. In doing that, we probably want to know, what are we putting it on top of? What are the denominator terms in this partial fraction expansion, and how do we identify those? What's a word that describes what's important or critical in this partial fraction expansion in terms of just writing it down? Is that too vague of a question? A little bit? If you're doing a partial fraction expansion, how would you do that? You would use A, B, and C. You would go back to elementary school and say my ABCs, right? That's fine, but now what are the ABCs on top of? What are they sitting above? The A, B, and C are these residues. Those are our partial fraction expansion coefficients, but we place those over something. We have to factor the denominator, don't we? We need to find what I was searching for was, where are my poles? Where are the pole locations? What are the values of S that cause that denominator to vanish? And those actually determine what my A, B's, and C's, or the A sub 1, A sub 2, and A sub 3 are on top of. Now, let's find where those poles are at. Pole locations, and those are the values of this complex frequency variable S that cause or allow D of S to equal 0. Those are our pole locations. And now hopefully you've written that down, because I may not be sliding back and forth too many more times, but I've already factored it into 2 pieces. The first piece is staring at us, and I hope that's pretty clean as to what we're doing with that, but let me just write down the denominator again. That was S plus 1 times S plus 2 squared plus 3 squared, and we want to find the values of S that cause that to vanish, and the structure that I'm using to write down that quadratic in the square brackets is special. That's a special form. That now screams at you where those roots are. The first one has already been screaming, isn't it? You can immediately find what value of S on the front end causes that. We should be finding 3 different S values, aren't we? Since you told me it was third order, we should find 3 different S values. The first one is when s plus 1 is equal to 0 or when s is equal to minus 1. And we might just, to make sure we're keeping track of those, we might just call that s sub 1. That's our first pole or first root. The other two need to come from that second piece, because if the second piece is equal to 0, then those would be values of s that cause that to vanish. Are there any real values of s that will cause that to vanish? No. The best we could do is put s equal to minus 2, and that gets us as small as we can make or drive that with real values towards 0, but it never equals 0. Let's then start playing with this expression. We could say, well, s plus 2 squared is equal to minus 3 squared. That's true, isn't it? Just subtracting 9 from both sides, where I'm writing 9 as 3 squared. Let me take the square root of that and realize that the square root of minus 1 is j in ECE terms. In math, it might be I, but I don't like to use the word I. That's a lowercase I. I like to stay in the third person. Sorry. So what do we have? We now have s plus 2 is equal to plus and minus j 3. And now we can find those values of s that are not real. They are complex that cause that to vanish. We just subtract 2 from both sides. And now do you see why I like to write that quadratic in that particular form? The minus 2 is right there. That's the real piece. And the imaginary, the imaginary component of those two roots are right there in the 3. So we now have two roots, one at minus 2 plus j3, and the other is at minus 2 minus j3. And now we have our 3 roots, our 3 pole factors that we'll put underneath A, B, and C. Questions on that? Those are our poles. We could now say, let's call S sub 2 minus 2 minus j3. Oh, let me put it there. Let's say it's plus. And then S sub 3 is minus 2 minus j3. We can now rewrite f of s in our partial fraction form, and now I'm not using a, b, and c, I'm subscripting the a's. Now I have a sub 1, a sub 2, and a sub 3. I will put a sub 1 over, that came from nowhere, s plus 1, that was one of our factors, plus a sub 2. Let me leave that on top of s sub 2, which is now s plus 2 minus j3. Is it clear that s sub 2 causes that one to vanish? We put s sub 2 of minus 2 plus j3, that's the pole that causes that factor to disappear. And now we have a sub 3 over s plus 2 plus j3. What I was trying to say is this one corresponds to that, and this one corresponds to that. And it's easy to get those confused because they basically, you're matching up two pieces that don't quite look the same, but they are the values that we want. In the complex S-plane, if we wanted to sketch these, there's that one. here is that one, and here is the third one. And is there a reason? Just so that we know, yes, there is a reason. Normally you would not put your poles on 3 different S-planes. I'm just trying to emphasize which factor goes with which root in the complex S-plane. It's very important that we associate A sub 2 with that factor that I've circled in or highlighted in yellow. That's critical, because we're going to find A sub 2 and we will derive our inverse Laplace transform from A sub 2 and not A sub 3. A sub 3 will end up being the conjugate of A sub 2. All we have to do is find A sub 2 and A sub 1 and we're finished with this partial fraction expansion. And that's why I'm trying to emphasize where these are with the 3 different S-plane poles. But typically, no, you would not be having all 3 of those S-plane pictures for one partial fraction expansion. You would put all of those poles in the same plane, S-plane. Did that answer your question? So that was the justification for why I did that. Let's now find these A1s, A2s, and A3s in this expression. How do we find A1? And this is for case 1. This is when we have distinct poles. And those are all 3 distinct, are they not? They're not lying on top of each other. How do we find A sub 1? We simply multiply every term by s plus 1 and evaluate what's left at the value of s that causes that denominator to vanish, which is s equal to minus 1. And all the terms on the right fall out or go away except for a sub 1. That stays by itself, and now we have a1 s plus 1 times f of s, and we evaluate that at s equal to minus 1. If we do that, we end up with 2s squared plus s plus 4. That was our original numerator. We have s plus 2 minus j3 and s plus 2 plus j3. That's the quadratic expanded in terms of my individual or distinct factors, and we evaluate that at s equal to minus 1. And sometimes it's actually cleaner to maybe, instead of playing with the complex numbers, just to realize that this is s plus 2 squared plus 3 squared. And then you can, down here, you can say, oh, that's minus 1 plus 2 squared plus 3 squared. You'll get the same answer. So that now I have 2 minus 1 plus 4 over 1 squared plus 3 squared. Or I now have 5 over 10, or a sub 1 is now 1/2. Let's now find, are there questions on that evaluation for a sub 1? Yes? How did I determine that all of these other terms on the right-hand side fell out, the a sub 2 and the a sub 3 factor, when I multiplied by s plus 1? If I multiply by s plus 1, it doesn't cancel anything in the denominator, does it? And I'm evaluating all of these at s equal to minus 1. So that just eliminates the a sub 2 term and the a sub 3 term. Is that clear? That's how that a sub 1 pops out by itself. And that's why doing case 1, which are the distinct roots, are easy or are straightforward. I'm not going to say it's easy, but it's straightforward. Now we're going to repeat that process for a sub 2. It's just now we have a factor that involves complex roots, but the process is exactly the same. So we're going to multiply everything by that factor, s plus 2 minus j3, and evaluate everything when that factor disappears for that particular value of s, which is minus 2 plus j3. That's our a sub 2. A sub 2 is now s plus 2 minus j3 times f of s. And what does that leave us? Well, the numerator we haven't changed, but the denominator, we've now canceled that factor. And we're left with an s plus 2 plus j3, and we're evaluating it at s equal to the value of s that causes that leftmost factor to vanish, which is minus 2 plus j3. Here's what I'm trying to say. The value of the complex variable s that actually causes the s plus 2 minus j3 factor to vanish or to become equal to 0. And now all we have to do is replace all of the s's with minus 2 plus j3. I have 2 times minus 2 plus j3 quantity squared plus minus 2 plus j3 plus 4 all over minus 2 plus j3 plus 1 times minus 2 plus j3 plus 2 plus j3. If you do the complex math, complex meaning you have complex numbers in the numerator and denominator, you will end up with minus 8 minus j21. Where is that point located in the complex s-plane? Just to give you a feel for that as a complex number. You just walk into the left half plane minus 8, and then you go down minus 20, or you go down 21 paces. That's in the third quadrant. So that should be, if you said magnitude and angle, that has a length bigger than 21. If you did polar, convert that to polar in my calculator, and you ended up with 10 at an angle of 25, you should know better, right? That's an incorrect, something went wrong. You plugged it in wrong. It's somewhere in the third quadrant, and so now you know it's a negative somewhere between 90 and minus 180, minus 90 and minus 180. The denominator is minus 18 minus j6, and when you are dividing complex numbers, it's usually easier or cleaner to put them into polar form. This is now 22.47 at an angle of minus 110.8. And the denominator is 18.97 at an angle of minus 161.6. Now we can take the ratio of the magnitudes, and it's going to be a little bit bigger than 1. It ends up being 1.184. And we can add 161.6 to the numerator and denominator's angle, or subtract the denominator from the numerator, and we end up with minus 110 minus a minus 161, so that's going to give us something around 50 degrees. And it gives us 50.8 degrees. Once we found a sub 2, we now have a sub 3, which is just the conjugate, complex conjugate of a sub 2. A sub 3 has the same magnitude. What's its angle? It's now minus 50.8 degrees. That's a sub 3. And we don't have to do any more complex math to find a sub 3 other than change the sign of its angle, because it was sitting on top of the conjugate factor that we started with. And what I want you to remember is that this polar notation is really a shorthand This is really the same or equivalent to 1.184 e to the j 50.8 degrees. And you'll want to make sure that you're paying attention to whether you're treating that angle as a degree or as a radian measure. Now we have our partial fraction expansion coefficients. We have 1/2 sitting on top of the s plus 1 factor, and we have 1.184 at 50.8. That was a sub 2 sitting on top of the pole factor associated with the pole in the second quadrant, which was s plus 2 minus j3 plus 1.184 minus 50.8 over s plus 2 plus j3. Again, I can't emphasize this enough, so I'm going to draw another diagram. Here's our S-plane. This is that associated with that pole. This is the pole in the second quadrant, and it is the pole that has a positive. I didn't give myself, oh well. Positive imaginary component. And that one is underneath a sub 2. That's the point I'm trying to make. A sub 2 is associated with that particular pole, which that's what you always want to be looking at. Your formulas in the book are going to assume that you now have used the residue or the partial fraction expansion coefficient associated with the complex pole sitting in the second quadrant when they start giving you the inverse Laplace transform pairs. That's the key point. Now, what is f of t, little f of t, if we now have capital F of s sitting up there? How do we inverse Laplace transform an s plus 1 in the denominator? That's e to the minus 1 t, scaled by that coefficient of 1/2. This is now 1/2 e to the minus t. If we did exactly the same process on the middle term to inverse Laplace transform it, we would have our scalar, which is complex, but we would write that down as 1.184 at an angle of 50.8 degrees. And what's it going to scale? It's going to be e raised to some s, and that s is minus 2 plus j3 times t. Isn't that exactly what we did in the previous inverse Laplace? We took 1/2, the coefficient, e to the s, which is minus 1, times t. And now we have an s that causes that middle factor to vanish, which is minus 2 plus j3. And then we can add in the next one. And that's true for t greater than or equal to 0, and I'm actually going to expect more from you on the exam. You can't stop here. If you stop here, you lose, I don't know, 40 points out of 20. Maybe not, but you lose a lot of points, okay? I'll be upset if you stop here, because now you've got complex numbers in your answer, and I can't deal with that. I just can't deal with that, okay? So I need you to put this into a real expression, and that's why I was trying to say that, in fact, that polar complex number can be rewritten as 1.184 e to the j 50.8 degrees. Let's now use that. So let's get a little closer, although it's still not what I want. So now we can say f of t is 1/2 e to the minus t plus 1.184 e to the j 50.8 degrees, e to the minus 2t, e to the minus j, or e to the plus j 3t, and plus 1.184 e to the minus j 50.8 degrees, e to the minus 2t, e to the minus j 3t. And again, that's t greater than or equal to 0. Now we're getting a little closer, still not there yet. 38 points out of 20 that you would lose. Trying to make a point, and you're not laughing. So maybe you're taking this seriously, which is important. We now have 1.184 e to the minus 2t. Those are all common in those last two pieces. And now let me collect what's remaining. I have e to the j 3t plus 50.8 degrees plus e to the minus j 3t plus 50.8 degrees. And now you should just be salivating or getting excited or something. You should just, your hand should just start writing now. Because what's in square brackets? Euler's sitting right there. He's just sitting there just smiling. Smiling at us. What's Euler tell us? Well, Euler tells us that cosine of x can be written in terms of complex exponentials as e to the jx That's Euler. He's just sitting there whistling because he knows that he can use this relationship to simplify what's in square brackets. I got so excited I lost my voice. But what we're doing, if we multiply by 2, we have 2 cosine of x is equal to e to the jx plus e to the minus jx. Now do you see why I was getting so excited? What is x? 3t plus 50.8 degrees, right? So now we can put it into a real expression without any complex numbers. We can now convert what we just had into an f of t that's now 1/2 e to the minus t plus 1.184, I'll do it in a couple of steps, e to the minus 2t times 2 cosine 3t plus 50.8 degrees. Or what you may see, or what you will start to just write down, is 1.184. Well, let me put that somewhere. Let me put the 2 out in front. I would put 2 times the 18184 e to the minus 2t cosine 3t plus 50.8 degrees for t greater than or equal to 0. And that's now a real function of time. And how long will it take before that disappears, that f of t? What's infinity? I don't know, that's way over. But what is infinity in electrical engineering terms? 5 tau, 5 time constants. How many taus do you have there? Tau. How many taus do we have? 2. Which one is dominating? Which one is the slowest? E to the minus t is half as fast as e to the minus 2t. E to the minus 2t is going to exponentially damp that cosine that's fluctuating at 3 radians per second with an offset in time of 50.8 degrees, and the e to the minus t will damp out a little slower. In this class, if I say, when can you expect this solution to be gone, you would say 5 tau. And then you would say, ooh, which tau? But you would say, I will take the smallest. Although they help each other, let's just focus on the smallest. The one closest, the pole closest to the origin, which has a time constant of, what tau, or what value of t causes that exponent to equal 1, or minus 1 if you don't factor out the minus 1. 1. Your time constant is 1. We need 5 of those. When will you be gone with this solution? 5 time constants, 5 seconds. After 5 seconds, if you wake up, you've missed it. Man, we'd miss a lot of lectures if they were that quick, huh? Or if infinity was 5 seconds, that's what I'm meaning. What is infinity? 5 seconds in this particular f. Is that clear? You only have to wait 5 seconds, and then it's done. What have we learned? Don't answer that. Let me just keep going. What are some observations? That we can make from this example? What was a sub 3 relative to a sub 2? They were just conjugates of each other. And if you now are confronted with a sub 2 over S plus alpha minus J beta, did I put a sub 2 over the right factor? Where is that value of S located that causes that denominator factor to disappear or vanish? Minus alpha plus J beta. That's in the second quadrant. So a sub 2 is in the right spot. Here is a sub 3, but I'm going to just call it a sub 2 star, or a sub 2 conjugate. This one is S plus alpha plus j beta. That's in the third quadrant. And what did we learn? Well, if we wanted to inverse Laplace transform that, that's just 2 times the magnitude of a sub 2 e to the minus what? With this particular alpha, beta, and a sub 2, what's the real damping term in this expression? It's the real part of the pole, and that's now alpha t. How fast is that cosine fluctuating? What's its frequency? Which term or which variable in that expression in the curly braces is going to help us with how fast cosine is shaking? That's beta, radians per second. Beta t, but then that's offset by some angle theta. But what is theta? Theta is just the angle of that complex number a sub 2. Here I'm saying a sub 2 as a complex number is the magnitude of a sub 2 at an angle of theta degrees. If you find a complex number for a sub 2, do you see how you can quickly write down the time domain expression and not have to go through all of those steps we've already gone through? You don't have to do that on the exam. You can just use this expression to immediately write down your answer once you have a sub 2 as a complex number in polar form. You need its magnitude and angle. This you should find in your textbook as equation 64 on page 447. And again, you will find it as one of the entries in table 3 of chapter 12 near the end of that section, which is page 451. That's what I want to say for case number 1 in this strategy for inverse Laplace transforms. What was case 1? Case capital I. Distinct roots. None of those x's were on top of each other. Let's now look at case number 2. Where we do have repeated roots. By this, suppose now that our capital F of s is some numerator, and I'm just going to write it as some generic polynomial, n sub capital 2 of s, s plus p sub 1 squared, s plus p sub 3, to emphasize that I really have, what's the order of my denominator? And if this has, if I don't have to do any long division, what am I assuming on n sub 2 of s? What's the order of n sub 2 of s? It's 2 or less. Is that okay? Needs to be strictly less than 3. I don't even want to talk about 3. I want to say 2, 1, or 0. It's s squared or s1 or s to the 0 in the numerator in order to inverse. And I'm just making that assumption now. I'm assuming that this f of s is strictly proper. What's my partial fraction expansion look like for this? How many terms would you expect to have? You would expect 3 since it's third order, but I only have 2 unique factors. Here is the order that I'm going to do it. I'm going to put A1 on top of S plus P sub 1 squared. Then I'm just going to start decreasing that power and continue to decrease it until I run out of s plus p1s, meaning I'm done for that being repeated twice, or repeated once. I have two roots at s equal to minus p1. And then I have a distinct root at minus p sub 3. And that's the strategy that we will use, and I haven't said whether p1 or p3 is real or complex. But I'm assuming that p3 is real. p1 may be real or imaginary. But in this case, let's just assume it's real to give us something to think about for now. How do I find a sub 3? That's exactly case 1, isn't it? I can continue to use what I just did for case 1. To find a sub 3, I'm just going to find that using the case 1 approach. So that now a sub 3 is equal to s plus p sub 3 times f of s, evaluated at s equal to minus p sub 3, or that's n sub 2 of s over s plus p1 squared, evaluated at s equal minus p sub 3. Now, we can do exactly the same thing for the coefficient that's on top of the highest powered factor of my repeated root. I can multiply both sides by s plus p sub 1 squared and evaluate at p1, or s equal to minus p1. It's only that a sub 2 that's giving us anxiety. Let's find a1 then, the same way we found a sub 3. Also, case 1, or the case 1 formula, works for the coefficient associated with the highest power of the root. And that, in this case, is a sub 1. So I now take s plus p sub 1 squared times capital F of s and evaluate that at s equal to minus p1. Which, the way I parameterized f, that's now just n sub 2, the numerator, over what's left after canceling the s plus p1 squared factor, which is just s plus p sub 3, evaluated at s equal to minus p sub 1. We now have 2/3 of those coefficients found. We found a1 and we found a sub 3. Now we need to find a sub 2. And there's a lot of different ways of doing that. And I'm going to try to work my way through some of those. So now, which one? This one. So now I'm evaluating this at the value of s that causes that factor that I pre-multiplied by to vanish, just like we've done before. Okay? And that one was disappearing when s was equal to minus p1. Then all the other terms are gone. Does that answer the question? So I think we now have a1 and a sub 3. We need to find a sub 2. A sub 2 we don't know, but there are many techniques for finding A sub 2. And now what I'm going to do is I'm going to assume that everything else has been determined in this example. I'm going to say one can assume, because we didn't have to know A sub 2 to find these other coefficients A1 and A sub 3. One can assume that A sub 1 and A sub 3 have been determined from the above technique. Which was case 1. Now, before we go through finding A2, let me just say what we are expecting to do once we found A1, A2, and A3. So this is an example with repeated roots. And suppose that I now have found capital F of S, which was, let's say, 2s plus 1 over s plus 1 squared, s plus 2. What's the partial fraction expansion look like in terms of unknown coefficients on the right? What's the structure? Is it clear where that came from? Now you will see when you start looking at some of the practice exams that sometimes I ask a question, I maybe give you capital F of S and I say, what's the structure of little f of t? If I say structure, that's a key word, and now that means, oh, he doesn't need me to find A1, A2, and A3. I just need to write down the time domain form for f of t, little f of t, in terms of A1, A2, and A3. If that's the case, what's the structure for f of t? Now, what happens when we have this factor squared or cubed? Now that introduces a new term into our inverse Laplace transform, and in fact, it's time. So now we have a1t e to the minus t plus a sub 2, and this one you already know how to do. What is that? That's just e to the minus t, and then we have a sub 3, and you already know what that does. And again, that's for non-negative values of t. Meaning this particular 2 is responsible for that t to the first power. This minus 1 right here is, or that 1 is the 1 that's sitting there between the minus sign and the t. This 1 right here is right there. And now I've run out of colors, but I'll go back to blue. This, maybe I won't, because I don't want you to confuse it with the 2 there. All right. This 2 is right there. Do you see what I'm suggesting you could write down for the structure of little f of t on the exam? You would just have to know how to partial fraction expand it. You wouldn't have to solve for A1, A2, and A3. Question? So now the question is, what if it's not squared but cubed? Great question, and I'm going to answer that in 3 lines. Is that okay? So really, to answer it now, that 2, I just take off 1 and I raise t to 2 minus 1. So now if it's cubed, it's t to the 3 minus 1, or t squared. So that's where I'm headed, but this was really just an aside for the structure. Or now let's just go aside. I guess this is sort of answering the question that was asked. A structure for repeated real roots. What's the generic structure? We just found that we had, let's say, 1 over s plus a quantity squared. What did that do in the time domain? I'll do the hard part. It was just t, wasn't it? Now, what if I did a cube? So now I had 3 of those poles sitting at s equal minus a. Now it's a little bit different. I have 1 over 2 factorial t squared, e to the minus a t u of t. So now I've changed it a little bit, but basically I end up with a t squared, but now I have to divide by n minus 1 factorial, where n is the power of the root. So in general, if we wanted a general formula, if you had an s plus a to the n, let's say, plus 1 power, now you have 1 over n plus 1 minus 1 factorial. That's why I put the n plus 1 there. I now have 1 over n factorial, t to the n, e to the minus a t, u of t. That's the general formula. And you might see that a different way in your book. This is like equation 1283 on page 450 that's now writing it a little different. They say, oh, if you have k over s plus a to the r, that's now going to be k over r minus 1 factorial t to the r minus 1 power e to the minus a t u of t. Do you see the relationship between those? They're exactly the same formulas. I just wrote the one in the blue box, a slight different variation on what you'll see in the book. But it's the same formula. Let's now look at a particular example. Suppose that we now have capital F of s, which is what we just had, 2s plus 1 over s plus 1 squared s plus 2. Structurally, we know the partial fraction expansion structure, the right-hand side. That's a1 over s plus 1 squared plus a sub 2 over s plus 1 plus a sub 3 over s plus 2. What's a sub 3? And why did I jump to that immediately? Because it's the distinct root. So I can multiply by s plus 2 and evaluate s equal to minus 2. So now I have 2s plus 1 over s plus 1 squared evaluated at s equal minus 2. Or I now have minus 4 plus 1, or minus 3 divided by 1, so this now becomes minus 3. And don't think that, oh, if I have a subscript 3, the coefficient is minus. Don't. I just now noticed that might confuse you. There's no correlation there, but it is because of this example. What's a sub 1? I'll spare you. I won't throw something as hard. I'll just throw a... That didn't come into the speaker, so we'll just ignore it. But this is now 2s plus 1 over s plus 2, evaluated at s equal to minus 1. Now we have 2 times minus 1 plus 1 over minus 1 plus 2, or minus 1.
I knew it!
Good intuition. Now, let's find Nemo. Let's find a sub 2. We need to find a sub 2. A1 and a sub 3 were easy. Maybe too easy. Now we're finding a sub 2, and I said before, there are many ways to find a sub 2. Here's one such technique, and I'm going to label this as select a convenient value for the variable s in our partial fraction expansion. So here is my partial fraction expansion. I already know a1, that's minus 1. A sub 3 is minus 3. I feel like a auctioneer pointing and getting bids. Now I need a sub 2. I can now replace s with a convenient value to find, that's the only unknown once I get rid of s, if I know a1 and a3. What would be a convenient value for s? 0. Because then the s's all go, don't they? I can't choose s equal to minus 1 because then I get infinity equals infinity. I can't use s equal to minus 2. Those are pole locations. Those give me nothing useful. So now a convenient value for s, in this case, could be 0. Then I have on the left-hand side, I have 2 times 0 plus 1 over 0 plus 1 squared, 0 plus 2, equaling a sub 1 plus a sub 2 plus a sub 3 over, 0 plus 2. And what do I end up with? I now have 1 upstairs and 2 downstairs. I have minus 1, I have a plus a sub 2, and I have a minus 3 halves. I have one equation and the one unknown, a sub 2. A sub 2 becomes 3. I had minus 5 halves. I add 5 halves to both sides. I get 6 halves, which is 3. Now I can write down f of t. I had minus 1 times t, e to the minus t, plus a sub 2, which is 3 e to the minus t, plus a sub 3, which was minus 3 e to the minus 2t, t greater than or equal to 0. And I would be done. But we can't pass up an opportunity to have some fun. We found a sub 2 one way. Let's find it a few more ways. So there was the first way with a convenient value of s, which in this case was pretty nice. Yes?
That would work if you had like S plus 1 to the third power. At all.
Yes, so this technique will work for, the question was, what if I had s plus 1 cubed? Now you would have, what would you have found? You would have how many terms on the right? 4. How many of those could you find using the case 1 method? 2. This is kind of difficult. So now we have 2 left. We found a1, which was on top of s plus 1 cubed, and we found a sub 4, which is on top of, let's say, s plus 2. Now we have 2 coefficients we have to find. Pick 2 convenient values for s. We need 2 equations and 2 unknowns. Is that? So you can't pick 0 and 0, but you can pick maybe 0 and 1. Not minus 1, but 1. And then you have 2 equations and the 2 unknowns. Did that answer your question? All right, so we wanted to find a different way. I'm sorry, a sub 2 a different way. Here is finding a sub 2. With a limiting expression. And here's the strategy. First, I'm going to multiply both sides of my partial fraction expansion expression with everything in it. I'm going to multiply both sides by the complex variable s. Then on both sides, I'm going to take the limit as s approaches infinity. On both sides. Then I'm going to solve for a sub 2. Let's see what that looks like in this example. I started with 2s plus 1 over s plus 1 squared s plus 2, and that was equal to a sub 1 over s plus 1 squared plus a sub 2 over s plus 1 plus a sub 3 over s plus 2. And I'm going to go ahead and assume that I have determined a sub 1. That was minus 1, and a sub 3 was minus 3. I have that expression. Now I'm going to do a limiting argument to try to find a sub 2, and that was to multiply everything by s. There's the s. That's step A. Now let me take the limit on all of those terms as s goes to infinity. So can I not write that in front of all of them and just sort of do it? What's the limit on the left-hand side as s goes to infinity? I have 2s squared, so concentrate on the highest powers of s. In the numerator, I have 2s squared. In the denominator, s cubed. I have s squared over s cubed. I let s go to infinity. That's like 1 over s going to infinity. That's 0. What's the first term on the right going to do as s goes to infinity? It's now s over s squared. That's now 0. What's a sub 2 term going to do? That goes to a sub 2, doesn't it? It's just infinity over infinity. They cancel, and now I have a sub 2. And what's the last term on the right doing? It's now minus 3s over s. As s gets big, those s's cancel each other, and I now am left with minus 3. That was pretty quick, wasn't it? A sub 2 is 3. Method 2. How about a third method? This one I'm going to call finding a common denominator. And this one you could start with and finish with, meaning you could find all three coefficients in one swoop. What we want to do is obtain a common denominator Then we simply compare coefficients or powers of S. Equate coefficients of like powers of S in the numerator, and then that's going to give you so many equations and so many unknowns. You solve the equations for the unknown coefficients. Let's see what that looks like. In our example, we started with 2s plus 1 over s plus 1 squared s plus 2. And that was equal to a1 over s plus 1 squared plus a sub 2 over s plus 1 plus a sub 3 over s plus 2. Now what I want to do is I want to put all of those terms on the right-hand side over the same denominator that's on the left. What happens when I put the A1 piece over a common denominator? What happens to the numerator piece associated with A sub 1? I now have A1 times S plus 2, and if I divided that out, I would end up with that first term on the right. Does everybody see where that came from? What about the A sub 2 factor? I have to pick up an S plus 1 and an S plus 2. And for A sub 3, and I can multiply these out, and I have s squared plus 3s plus 2. I have s squared plus 2s plus 1. And now if I distribute those a's across everything, do you see how I can compare coefficients with the right-hand side and the left-hand side? I would now have what is going to multiply s squared? On the right, I have an a sub 2 and an a sub 3 times s squared. And those must equal zeros because there's no s squared term on the left. And on the right, I need to find the coefficients that scale s. I have a1 plus 3a sub 2 plus 2a sub 3 times s. And then I have a constant coefficient, which is 2a1 plus 2a sub 2 plus a sub 3. And if I equate coefficients, if you give me just another minute, we'll be finished. Thank you. Keep going. The s squared we've already done. That was 0 is the a2 plus a sub 3. The S1 coefficients on the left, I had 2, and on the right, I had this A1 plus 3A sub 2 plus 2A sub 3. And then if I compare the constant coefficients, or the S to the 0, I had 1 on the left, and I had 2A1 plus 2A sub 2 plus A sub 3. And now I can set that up in an algebra relationship. I have 3 equations, 3 unknowns, invert the 3 by 3 matrix, and I immediately then have A1, A2, and A3. Thank you. We'll pick up the fourth method for finding A sub 2 is in the book. It's by differentiation. I don't know if we'll cover that or not.